Good morning, students. Our today's topic in the subject of physics O levels is general properties of waves. So concentrate yourself. This is a tough topic, a conceptual topic. A lot of formulas, concepts, techniques will be used in this topic. So concentrate yourself. We are going to start now. Energy is often moved from one place to another by waves. No matter is transferred in the process. You can see this. If you throw a stone into a pond, waves spread out from the splash, and soon the water at the edge of the pond moves as it gets some of the energy of the splash. So very important point to be remembered. Energy is often moved from one place to another by waves, but no matter is transferred in the process. Kinds of the waves. There are two kinds of the waves. Number one, transverse waves. In transverse waves, particles' vibration is at right angles to the direction of the wave. So if this is the direction of the wave, the particle will move at right angle to the direction of the wave. You can see that energy is moving down the spring, although each bit of the spring is only vibrating. It is vibrating at right angles transversely to the spring. So here is a spring. When a spring is moved like this, okay, the energy is moving down the spring, although each bit of the spring is only vibrating. Each bit of the spring is only vibrating, but energy is transferred. Look now from here to here, and then will be there. Okay, radio waves, microwaves, infrared waves, ultraviolet rays, X-rays, gamma rays, water waves, and light waves are the examples of the transverse waves. Here is a question. The diagram shows a ball floating in a tank of the water. Which direction show the movement of the ball when the wave passes? So here is a ball. The wave is passing through it. Which direction diagram shows the movement of the ball? So the ball will move transversely at right angles to the direction of the wave. So D part will be the answer. So D, water waves are transverse waves. Number two type of the waves is longitudinal waves. In longitudinal waves, the particle's vibration is along the direction of the waves. So if this is the direction of the waves, the particle vibration is along the direction of the waves. If you look closely, you can see again energy is passing down the spring, although each bit of the spring is only vibrating or oscillating. It is vibrating lengthways or longitudinal. So the particles move like this. In transverse waves, particles move like this to the direction of the waves, but in longitudinal waves, particles motion is sideways along the direction of the waves. And this is called oscillating or vibrating. It is vibrating lengthways or longitudinally. Sound waves are longitudinal waves. And here is a video of longitudinal and transverse waves.
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves.
So here you can see the particles are moving lengthways to the direction of the waves. This is a longitudinal wave.
In a transverse wave, the disturbance that makes up the waves.
Whereas in transverse waves, the particle's motion is at right angles to the direction of the wave.
Perpendicular to the direction in which the wave travels. Minute.
Okay, moving further. Here is our question. A lightly coiled spring is fixed at one end and held by a hand at the other. So this is the fixed end and this is the end which is held by the hand. Which hand movement causes first a compression? So compression will be like this and then a rarefaction. Rarefaction is the pulling. Compression is pressing and rarefaction is pulling to travel along the spring. So, okay, first compression. So definitely that will be towards right and then left. So D option is right. So look now. D, a longitudinal wave is a wave such that the vibration of the particle is along the direction of the wave motion. To produce a compression, the spring should be compressed. For a rarefaction, the spring should be pulled. Okay, the next topic that we are going to read in the lecture is the ripple tank. We can study transverse waves by using water waves in a ripple tank. Put some small pieces of the cork on the water in a ripple tank or your bathtub and move the wooden bar up and down to make straight waves. So here is the wooden bar. Move wooden bar up and down to produce the waves. The piece of the cork will move up and down at right angles. These are transverse waves. Here is a side view of the transverse wave. So this was the normal position of the wave, that is dotted line. And here is the highest point of the wave, then the normal point, and this is the least point, the lowest point of the wave. Okay, the high parts are called crest and low parts are called troughs. So this is the high part of the wave and this is the low part of the wave. High part is crest, low part is troughs. The distance marked A is called amplitude. So amplitude is the distance between the average wavelength and the highest part of the wave. So this is the distance A, or it will be definitely equal to the average distance, average wavelength, average level of the wave and the lowest part of the wave. So this is the amplitude. It is the height of the crest above the average water level or the depth of the trough below it. The line joining all the crests or troughs of a moving wave is called wavefront. So if we join the straight line, all the highest part of the wave or all the lowest parts of the wave, that will be called wavefront. Any two crests or troughs are in phase because they are moving in the same direction with the same speed and having the same displacement from the rest position. The speed of a wave is the distance traveled by the wave in 1 second. This is called the speed of the wave. This is the distance traveled by the wave in 1 second. The time period of a wave is the time taken to produce one complete wave. So these are the definitions which you have to remember because these definitions come in the paper number 2 as well as many MCQs from this topic come in paper number 1 of physics. So you have to remember all the points. So the time period of a wave is the time taken to produce one complete wave. The number of the waves passing through a point in 1 second is called frequency of the wave, represented by small f. So it is the number of the waves passing through a point in 1 second is called frequency. The relationship between the time period and the frequency is given in the following equations. So F is equal to 1 over T. So this is the relationship between the frequency and the time period. In case of the transverse waves, the distance between two successive crests or troughs is called the wavelength. So here you can see the distance between two successive crests or two successive troughs is called the wavelength. In case of the longitudinal waves, the wavelength is the distance between two successive centers of the compression or rarefaction. So here are two successive compressions. So the distance between the centers of the two successive compression or the distance between the centers of two successive rarefactions is called wavelength. One oscillation is completed when the pendulum bob moves from A to B and then back again to A. So look now, if bob go from A to B and then back to A, this is called one oscillation. The frequency of a wave is the number of the complete waves produced per second. If the wooden bar or the piece of the cork in the experiment moves up and down through two complete vibrations in 1 second, then the frequency of the vibrations is 2 cycles per second. This is also written as 2 Hz or 2 Hz. So read again. In an experiment, if the wooden bar or the piece of the cork moves up and down through two complete vibrations in 1 second. So that's why the frequency of the vibrations is 2 cycles per second, written as 2 Hz or 2 Hz. A wave which vibrates only up and down like this is said to be polarized vertically. Wave speed formula is frequency multiplied by wavelength. Take note, move the wooden bar up and down at a low frequency first and then at the higher frequency. So this is a very important point. If you move the wooden bar first slowly and then speedily in water, you can see, look now again, move the wooden bar up and down at low frequency first and then at a higher frequency. You will see that there will be 2 points to be noted. Number one, the speed stays the same. But when the frequency increases, the wavelength decreases. So here you can see speed is increases. So that's why the wavelength will be decreased. Okay, here is another question. Sketch 1.5 cycles of a water wave and mark on your sketch the amplitude and the wavelength. So here is the correct wave, water wave, and this is wrongly sketching by a student. So this is the correct one. Okay, on your sketch, the amplitude and the wavelength. So the distance between two successive crests is the wavelength, and the distance from the average height of the wave to the highest front of the wave is called amplitude. So look now, correct amplitude is this one from here to here, and this is the correct wavelength from here to here between two successive crest or two successive troughs. The next topic that we are going to read in the lecture is reflection. Reflection at straight mirrors. So there will be two cases. One, reflection at the straight mirror. Second, reflection at the curved mirror. So first we are going to read the reflection at a straight mirror. Place a straight metal or plastic barrier in the tank so that it reflects the waves like mirror. So here the straight piece of the plastic or metal will be placed in the water tank. Send single waves across the ripple tank and look carefully for the waves reflected off the mirror. It is following the rules of the reflection. That is, the angle of the incidence is equal to the angle of the reflection. So when it will strike here, the angle of the incidence will be equal to the angle of the reflection. Second case which we are going to read in the reflection is reflection at a curved mirror. Place a curved barrier in the ripple tank. Again, send single waves across the ripple tank and look carefully for the reflected waves. So here is the curved mirror that is placed in the ripple tank. Okay, the waves are converged to a point called the focus. When the waves will strike the curved mirror, they will come back and will be focused, will be converged at a point called the focus. Okay, the reflection with a curved mirror turned around the other way. So now the curved mirror is placed in this way. This time the waves are spread out or diverged by the mirror. So when the waves will strike at the curved mirror in this shape, they will be spread out or diverged. So here is a video that will make your concepts more clear. So this is a ripple tank. Waves are sending here. This is the, so here you can see the movement of the waves. Here is the mirror placed. So these are the waves. Look here now. The next topic that we are going to read in the lecture is refraction. Place a thick sheet of the glass in the tank and adjust the depth so that the water is very shallow over the glass sheet. Send waves across the tank and look at the waves when they travel through the shallow water. What happens to the speed and the wavelength of the waves when they move into the shallow water? So here is a thick sheet of the glass or plastic is placed in the ripple tank, and at this stage water is very shallow. Now place the sheet of the glass at an angle and repeat the experiment when waves change their speed and direction like this. We say that they have been refracted. Sound and light waves can also be refracted. So this is an angle to the sheet. So the waves will be now refracted like this. When waves move from a region of deep water, here is the deep water, to the region of the shallow water, and here is the shallow water, the frequency remains unchanged as it is source dependent, though the speed and the wavelength will decrease. So this is the point to be noted, that when the waves move from deep water to the shallow water, frequency will remain same, but the speed and the wavelength will decrease. The wave speed equation for deep water and shallow water are V1 is equal to F lambda 1 and V2 is equal to F lambda 2 respectively, with here in deep water speed will be greater than the speed in the shallow water. Also, the wavelength of the deep water will be greater than the waves in the shallow water. The next topic that we are going to read in the lecture is diffraction. Do waves change shapes as they go through a gap in a wall? First topic that we are going to read in the topic is wide gap, and then we will read the narrow gap. So first the wide gap. when the waves will pass through the wide gap, what will happen? So look now, use a ripple tank to send straight waves across water to wide gap between two barriers. So here are two barriers. The waves travel almost straight on, rectilinear propagation. There is a clear shadow behind each barrier. So look now, there will be a clear shadow. Now the narrow gap. Now send straight waves through a narrow gap. The waves spread out after passing through the gap. This is called diffraction. Diffraction is almost obvious when the width of the gap is about the same size as the wavelength of the waves. So look now, they will be diffracted. Sound waves are diffracted through doorways because the wavelength of the sound is almost the same size as the door waves. Doorways. This is one reason why you can hear people without seeing them. Light is seen to be diffracted only if it is passes through a very narrow slit. This shows us that light is a wave motion with a very small wavelength. And here the diffraction of the light will be shown to you people through a video.
Diffraction of light. A ray of light bends slightly as it passes around the edge of an object. The phenomenon of bending of light from its straight line path around the corners of an obstacle or slit is known as diffraction. Diffracted light can produce fringes of light, dark or colored bands. Drag the slider to observe how the quality of diffraction changes with the change in the size of the slit.
Here is the size of the slit. Look at the shape of the waves. Now the slit is opened. Look now, size is widening. Look at the shape of the waves. Look now.
We observe that the process of diffraction becomes much pronounced when the dimensions of the slit are comparable to the wavelength of light. Optical effects due to atmospheric diffraction of light. An optical effect that results from the diffraction of light is the silver lining sometimes found around the edges of clouds. Coronas surrounding the sun or moon are also caused due to diffraction. The illustration shows how light from the sun is bent around small droplets in the cloud. At times, diffraction of sunlight in clouds produces a multitude of colors. This optical effect is called cloud iridescence.
So these are the effects of the diffraction of the light. Okay, now radio and TV waves can also be diffracted. Radio waves, longer wavelength, can diffract round the hill to be received by the house, but TV waves, short wavelength, do not bend as much. The house will have poor TV reception. So radio waves have longer bend, but TV waves have short bend. That's why the house to the other side of the hill will have poor TV signals but strong radio signals at the same time. So this is red line, that is radio waves, and this is shorter lines, these are TV waves. So the next topic that we are going to read in the lecture is wave evidence. Sound, light and radio signals all undergo reflection, refraction and diffraction. This suggests that they travel as waves. For example, so here are some evidences. Light reflects from mirrors, sound reflects from hard surface, light bends when it passes from air into glass or water, sound bends round obstacles such as walls and buildings, which is why you can hear round corners without seeing the people. Light spreads when it passes through tiny holes and slits. This suggests that light waves must have much shorter wavelengths than sound. And some radio signals can bend round very large obstacles such as hills. This suggests that radio waves must have long wavelengths. So these are the evidences which prove that wave evidence is there. So sound, light, and radio signals undergo reflection, refraction, and diffraction. And finally, we are going to read some very important points. Gamma rays have the shortest wavelength and the highest frequency in the electromagnetic spectrum, whereas the radio waves have the longest wavelength and the shortest frequency in the electromagnetic spectrum. Visible light is just one of the 7 members of the family of the electromagnetic waves. All the electromagnetic waves travel at the same speed of 3 multiplied by 10 raised to power 8 meter per second in a vacuum. Periodic motion is the motion that repeats at regular interval. So that kind of the motion which repeats itself after regular intervals is called periodic motion. One complete periodic motion from one extreme point to the other extreme point and back is known as the oscillation or a vibration. So this was the topic, students. Read this lecture again, understand it, learn it, and make your notes. Thank you so much.